Yeah, welcome everyone for High Performance Computing, Lecture 7, Hybrid Programming and Patterns. So the material of this lecture combines everything we learned around MPI, but also what we learned about OpenMP. So this is what some people would say refers today to hybrid programming, so that you basically have a C code or even Fortran that we will experience today. That actually use both of these programming paradigms in parallel. So combining distributed memory with shared memory. And of course, this is quite complex, as we will experience throughout this lecture. And then also, basically, a very important part of this is what people consider today as hybrid programming, also is combining the power of GPUs. So GPUs is something we didn't really looked at in detail yet. It will come in lecture 9, but still take away the message that there could be also hybrid programming in the sense of combining CUDA when you use NVIDIA GPUs, for instance, with OpenMP and with MPI, and we have even an example today in our lecture. So in the end, you will experience that essentially this hybrid programming is very complex, especially if you take away the message that this is parallel. It uses different languages, different ideas how to program. And also, of course, this all has to have some purpose. We do this not for fun. We do this for science or engineering problems. Hence, there's a domain-specific aspect all about it, which means some physical formulas, numerical methods that we also will look into a little bit when we think about certain patterns. However, certain patterns are also interesting when you think about stencil methods. But however, before we go into the material of lecture 7 today, which is quite interesting and also at the same time quite complex, let us review what we learned the last time when we had really a very practical lecture of, basically OpenMP in practical lecture 6.1, where we really used OpenMP in different ideas of applications. And we initially learned that essentially, really this is this master thread that's always alive and then spawns here so-called different threads in these parallel regions to do some work in parallel. And we also learned that, of course, OpenMP is in the realm of shared memory. So this is really something where you are limited by, of course, the amount of memory you'd have then within the node. And essentially this master thread at some point in time will basically fork some threads, as we see here. And then essentially we will have a join again, but the master thread will always be alive. But we also learned, also in the theoretical lecture 6 about OpenMP, that the master thread is of course part of the game. So he's also basically one part of the tackling problems with different work chunks that we learned, and is basically not something which is considered maybe just as a master thread in terms of management. So you could consider him as a worker too, basically spawning then just helper threads. The modus operandi, how you really would program an OpenMP program, is not that far away from what you learned already from MPI. So we'll see that essentially what we have is that we have a Hello Thread C program, and you see we include here, instead of the MPI header, then the OMP header here. And of course, a valid C program is needed when you want to have a valid OpenMP program. So this is the first part of the game. And you see here an example of one of these so-called sentinel of this pragma statement, people would say, which enters now exactly what we have here, a parallel region, right? Now you also see that here we have 3 threads, here we have 4 threads, here we have just 2 threads. Here also you see, combining this with the source code on the right-hand side here, I don't see any of this. So there's no thread number. And this is exactly what you learned also. Essentially, shared memory should be programmed in a way that the threads are not really known, right? So this is something, if you remember, is what we want to export as part of the environment variable OpenMP num threads here, 16 as an example, but which is not part of the program. So it really depends on which system you go, how much threads you would be possibly employ, how your domain decomposition would basically support this. There are lots of different elements to it that we cannot go all into details. However, we also learned, compared to MPI, that it's quite interesting that we can actually identify threads. So similar like we learned in MPI with a rank, we have also a thread ID. And this is what the OpenMP environment gives us as soon as I enter a so-called parallel environment. We learned some construct like this private TID, which means essentially that every thread has also the possibility, although it's shared memory, also to have a, let's say, private memory space, saying that this thread ID is, let's say, very different in all the different threads, which enables us to really then identify that I am essentially thread 0, I'm thread 1, I'm thread 2, I'm thread 3, etc. So by identifying essentially the thread ID, we are also able to basically use this information to influence the source code and the program flow, as this example shows us. You remember from the Hello World program, it's a very trivial program here that you see that only here the master thread ID 0 is basically getting the information of all the number of threads which are available and prints this out. So we would say that this hello world from threads should be 4 times existing because we are in the parallel region, and I specified maybe 16 or I specified 4 as this particular example of the output gives us here. Number of threads in parallel region is 4. So I have actually 4 threads saying hello world from thread T0 till T3. But then, of course, only one of the threads is considered to give us the overall number of threads. This was an interesting example because it really reflects on the ideas that we had on MPI, but always remember that MPI is very different in the sense that it's really doing distributed memory. So OpenMP is about shared memory. And this is what we learned in lecture 6 as well. Now, interestingly enough, we use essentially the C compiler also with a specific flag of OpenMP. And when we then have this hello threads executable, we use it very similar as we have done essentially here in this statement, the executable in the batch script. However, we have to make sure that we have certain tasks now that are actually backing up the number of threads and basically have a little bit of more fine-grained situation. Now today, when we have hybrid programming, we will learn that we need to combine this now. So we need, let's say, more nodes because we want to maybe have distributed memory across different nodes, but also want to take advantage of shared memory within a node. And this is, of course, the idea then of one of the ideas of, let's say, hybrid programming without, leveraging yet GPUs with CUDA and so forth. So, however, the scheduler is executing it, and when we then have the outcome that we already know, similar, exactly like we have done in the MPI program, we assume that the output is like our Hello World program was saying us. So this is all very similar. However, how the compiler treating the source code is a bit different. You have to see that this is a compiler directive, so it informs the compiler what's going on in order to really do this parallel computing. While in MPI, we explicitly had MPI send receive, we had MPI broadcast, MPI scatter, and all the different MPI operation from MPI init and so forth. So this is a quite interesting endeavor here that we basically see, and also shows us that really the parallel computing in the end, of course, follows the same idea. You have a certain part of the source code that should be in parallel executed. I want to identify different elements of the parallel computing, which is a rank on MPI, but also maybe a thread in OpenMP. We carried on to many different work constructs, as it is called. And of course, I don't want to repeat the whole lecture here, but I think one of the most important ones and the most important in terms of simplicity is really this parallelization strategy of doing a fork in context of some certain loop construct. So essentially, you see here some source code that we tried, which gives us an interesting view also on the idea of basically using dynamic chunks, but also gives us an idea of a for loop that we just parallelize here. So within a parallel region that we see here, there's a certain number of threads that is actually then steered by this job script. We will then execute essentially this parallel this part here, and this will be executed in parallel. We will give out how many parallel executions are there in terms of number of threads. We initialize, however, not in parallel here for the master thread, the arrays A and B. And then we see essentially that C is very independent parallel, right? Again, I repeat this. Think about that CE equals AE plus BE is essentially completely independent from all other like E plus 1 or E minus 1 iterations of the loop. And this is a beautiful example of how you can use OpenMP and basically just do essentially these elements of the for loop as, you know, different chunks that you define. You see here the overall array of it is basically 1000. We had here an example chosen of the chunk size of 100. And this means that basically we have a dynamic scheduling on the chunk size of these different arrays. And how that will look like then in the dynamic fashion could be something like this. You see that here, instead of static, we have really a dynamic idea of when once basically this has been done, because maybe the addition was very simple in some cases and a bit more complicated in others. We see that there's not really always a homogeneous assignment of the different threads. As soon as basically a thread is ready to receive more work, it will get another chunk to work on in order to execute this basically loop in parallel. And these are the modifications you can do. However, you see also with a couple of statements, you have already parallel computing. And this is only in the shared memory, of course, now possible, because in the send receives and the MPI world, as we already know, we really have to make sure to copy different arrays, copies different data structures in order to also send those and receive those and have, let's say, space allocated for it. All of this is essentially not here required because we immediately operate on the real array or on those entities that we say here it's a shared array of A, B, and C, but also the variable chunk is essentially shared. And with this, we basically have just the private E, which is then the kind of index of the different loops, of course, which should be a little bit private to each of the threads because they will have their specific chunks where they work on. So this is an interesting way of how to program, let's say, in a parallel fashion. We also know that it is not easy to do it when you think about combining it now with MPI, which brings us now essentially to the lecture today, what happens when we talk about hybrid programming and also patterns. It's more a theoretical and conceptual topic because we also want to integrate a very much higher view of what is possible in parallel computing. We will reflect on some patterns, which we will see again materialize when we go into all the different applications later on, because they will pick up certain patterns which are very eminent, basically from stencil methods up to different domain decompositions in the terrestrial systems, and actually then also coupling codes in different areas using halo regions. All of this could be considered different patterns, but also PDEs, partial differential equations, or numerical methods in general is something which we consider patterns, where we give a small introduction here as part of this lecture, but we'll come back to those also when we then have our more application domain specific lectures later on. So the structure of this lecture is really starting with hybrid programming in a very traditional fashion. That means we want to understand why at all we want to have this complexity, why we want to combine MPI with OpenMP. What are the memory benefits? What are the different options how I do this, right? There could be hybrid systems with a so-called vector mode or task mode, and we will basically have some lessons learned reviewed of what we can recommend to do best if you do hybrid programming. However, take away the message, this is really already a very advanced topic. Hence, you don't do hybrid programming very much in your assignments. But that is something where you can, of course, very fine-tune your application and get some results, as we have already basically alluded to when we are talking about the HBDB scan algorithm. We will also reflect a bit in this lecture. A new form of hybrid programming is considered to be also using the graphical accelerators together with CPUs. So basically, you have these two entities. You know that a little bit from lecture 1 already. You would have the device memory of the GPU, but also the normal memory at the CPU. And both are processing entities at GPU and CPU. So why keeping them, let's say, idle while one is working? So of course, many codes these days, actually what we also have to review later on in our application codes, is again that people want to use CPUs and GPUs in parallel, right? And keep them both busy. And this gives another order of magnitudes of complexity, because now you have to program GPUs, you have to think about the memory, filling the memory with to-dos, with work from the devices of the accelerators, while also keeping the CPU busy. Keeping the CPU busy can mean over different nodes. So you want to distribute it maybe with MPI and still within the CPU and node structure with other CPUs, you want to have shared memory. So essentially saying that the ultimative, let's say, peak of do hybrid programming today would be implementing CUDA maybe on GPUs, combined with MPI and OpenMP hybrid codes on CPUs. And this is a really loaded element, and we will come back to this in some points of all the simulation sciences and data science applications in context that is basically there, and also give some recommendations that only do this path if you're really sure you want to do this. So if you see, for instance, that the MPI scalability breaks down for some reason, or you want to reduce the size of Halo regions, there are different reasons why you want to do, let's say, shared memory and distributed memory programming in parallel. But sometimes the more seamless way to do, also in the light of the scalability today towards exascale, right? That we have a lot of systems and nodes available. Maybe an MPI pure code might be much better than entering in the complexity of shared memory. But this is, of course, a complete application domain question that we cannot solve here as part of the course. The second part of this lecture then will going into so-called patterns, which is only indirectly related to hybrid programming, but of course here and there helps a little bit to understand the complexity when doing so. But of course the patterns are something which are not necessarily requiring hybrid programming. So there's things like nearest neighbor communication, Cartesian communicators you already know from some of the MPI lectures and one of your assignments around the ocean. Then we will review some patterns, so-called stencil-based methods and iterative methods, which are really often used and applied in different areas of sciences. So you could call them a pattern. It's not directly like the design patterns you may know from software engineering. So this is a bit more loosely defined, but it's something what many scientific and engineering applications just use in a very similar way. That's why we basically refer to this as patterns here. And this is, of course, the same with working with Halo regions, working with numerical methods, numerical approximations, because usually what we want to do is in simulation sciences to be as best real as we want, because, or as we can, because we want to simulate the reality and we want to simulate and explain what the physics are doing. But on the other hand, the problem is that the physics is so tough to solve that we cannot actually do it right away. We have to have some approximation in order to get basically the ideas of computing it. And we will come to this as part of the second part of this lecture today, also then understanding a little bit the moving parts when it happens with partial differential equations. So we want to simulate something over time. Of course, not a static idea of something, or let's say a terrestrial system, for example. So this is something where we also learn that those patterns, numerical methods and PDEs are incredibly important also when you think about simulations over times today. So we really give then a terrestrial system example. We have another lecture on this, which goes much more in detail, but it captures really the essence of showing you why those patterns are needed when we want to go towards realistic simulations in basically HPC. And with this, you basically have lots of different elements learned. You really have one of the most complex aspects of parallel programming learned today, hybrid programming. I could assure you that basically there's nothing more tough, only maybe one part of it, and that would be assembler programming. So this is a very low level and also very, let's say, complex. But if you think about from parallel programming on the, let's say, a little bit higher level, combining OpenMP with MPI and then also on top of it GPUs with CUDA is really an extremely, incredibly complex aspect of parallel programming that you will learn. You have some HPC environment tools that, of course, support this. The OpenMP environment and also the MPI environment itself will basically enable you different tools to also work together from, let's say, different processors together with threads to enable this hybrid programming, because we will run into problems with thread safety and elements that we quickly review here. But of course, the environment tools like the MPI environment also gives you some programming support for this. And this is also, let's say, something you can take away how you do HPC programming paradigms. So you really use here distributed memory, shared memory, and accelerators in some of the examples. So these are computing paradigms which are completely different from each other, but you combine their strength in order to solve a scientific or engineering problem. So let us start with hybrid programming. And this is a lot of catching up what we had in the beginning part of the lectures. You remember when we had hybrid systems, we already motivated this a little bit of saying MPI use a lot of buffering techniques to transfer data. You learned this by now. It is required because you essentially copy the data to be essentially then sent to another node, and you have to make space for it to also get data from another processor, right? Because essentially you have no access to any memory from the other processor. Then in this sense, you actually have this multiple memory copies to get anything from A to B. And this is, of course, quite some footprint. And this is essentially something where an advantage of shared memory techniques could be really there, where basically OpenMP threads can really read memory on the same node. So basically on-node communications with MPI, let's say, is not really recommended. It doesn't make sense. It is just an overhead. You see that here a little bit explained. We are within the realm of one node, and still we use MPI here for sending one, let's say, a block of data in via the memory, then of course, by having this different multiple memory copies to another processor within the same shared memory space. So we would end up with multiple memory copies, and this makes absolutely no sense. So when you program hybrid systems, you would go a complete different path, right? You would have essentially the shared memory nodes, which you have here, and we just explained, combined with a very strong communication network. It could be gigabit Ethernet, but also, of course, here and there, InfiniBand, which is very strong and very, let's say, a very high performant network to basically send messages between the different nodes, where MPI makes much more sense. Within the node, then, we have learned it doesn't make sense to further use MPI. So here, when you really want to leverage all the available memory or leverage all the different processors and fine tune with different threads, then it makes sense to employ OpenMP within the node while you exchange data across the different nodes. And essentially, this is the idea then of programming this hybrid systems in a very simple way. Simple in the sense that in a way that is quite of given how you do it for MPI, because you would only use it for explicit internode communication, and then of course for the OpenMP within one node. And this sounds so trivial, but you have to always think about that, of course, that you have to combine it with domain application problems. And there, of course, the problem comes in. And usually what people would say is a pure MPI program for parallelization is still, let's say, the way to go, especially if you think about scalability. And only if you see that the MPI scalability maybe breaks up at some point in time, then is really an idea of doing shared memory more. And of course, what we also see from the experience today is that people think about this differently, because now we have also accelerators. And this is a movement of many application codes that go, let's say, from a traditional way of MPI, and then did in the past maybe some OpenMP tunings to it, and they move now more or less to accelerators, so CUDA versions. Now, since we have also AMD Radeon and other cards coming up, so other accelerator technologies, this will be getting also more complicated, because CUDA will not remain the only accelerator programming paradigm anymore. So you can see that instead of having one standard like MPI and OpenMP, you basically require other standards to program then the accelerators. And this is something which we will also learn in lecture 9 when we talk about then these areas. Some challenges, of course, are then when you do really this combination of these paradigms with MPI codes is really where basically are your kind of processes positioned, right? It really depends on the association of threads and the processes to the cores. It also depends on which patterns you use then on top of this, basically. So, for example, the stencil methods that you see later, where we have nearest neighbor communication, for instance, this supports parallel programming, but you can also think about other challenges that is not so easy, like maybe tree-based methods and so forth. So this gives us already a kind of glimpse that essentially programming hybrid systems is not as easy as it sounds. You would have here the illustration of what I already alluded to. Essentially, you have this idea of an MPI send and receive that you do across the different nodes. And then essentially within the OpenMP, you kind of doing then the shared memory programming. Often the rewards, however, are good in performance, as we have seen in HPDB scan. So when you do it well, which requires some work and also some tunings using perhaps performance analysis tools that we will allude to in lecture 8 coming up. This, of course, can give you some memory benefits. And this is, of course, depending on all the MPI process you employ that have, let's say, different, it's processes really, right? It's not a thin thread. It's a thick process. It has, let's say, memory space for data, a heap and a stack needed for processing. And then when you think about the threads, they're very thin and very, let's say, efficient in the end. So you would save a lot when you use threads instead of processes. You, on top of it, save then the buffer space that we learned for the communication of each individual processor that basically needs for IO to buffers, but also for the communication between the different processors, always as buffers to communicate. And then what we really have is that, of course, the memory requirement overhead from these different multiprocessors is basically an idea of getting a more streamlined way of access to more memory per process in applications. In other words, saying that, of course, using hybrid programming is essentially giving you maybe a better utilization of memory, really, when you're doing this, of course, while since sometimes maybe a node is not really exploited in terms of all its memory, just to scale well with MPI, you have, let's say, a system allocated with a big chunk of memory in a node, but you really don't completely use it. And this is, of course, also for the utilization of a system, not really nice. But on the other hand, we will learn that it's computing and programming is quite complex. So you always have to have this trade-off, what you want to do. Here's a very simplified way of seeing this when you have a very simple example of a hybrid system. We also learn that the MPI init here has a specific support for using threads. If you remember, the MPI init was always very different. It was not an MPI init thread that is actually then gives you some ideas of how you can do so-called directives for thread safety. So thread safety I will cover in the next slide. Just see how that works when you now combine MPI. You would have still the general modus operandi of MPI com size, MPI com rank. You have your different, let's say, ranks inside this world. You have this number of processes you define. So this is all what we know. We do our typical MPI operations or collectives here. So essentially, it's a typical valid MPI program. However, we also can combine it then, as you see here, with a pragma statement of saying for some idea, could be a loop, could be something else. I really want to do some shared memory processing, which then will remain within essentially the idea of the node, right? And then after this is collapsed or basically joined, again, then I can be back into MPI space until I do my MPI finalize, maybe with a gather here, in order to get really then again, MPI working with a collective operation. And this is something where we now have to be a little bit careful when we think about the so-called thread safety. But a way to visualize this is a little bit like this, that you see in typical MPI programs that we learned. We had a processor, it has its lifetime, which was always, let's say, very simple. And of course, we had this message exchanges between them. And when you think of combining MPI with OpenMP, you have still, of course, the processors. They will not move away. But instead of having this process with one lifetime, you have, let's say, one processor with a lifetime that always spawns up then essentially different threads as well. So you have this basically combined in order to exploit then one node in terms of doing this. And of course, there could be different ways how you combine this. We will learn this with the different modes that you have, but this is really an easy way to understand it. When it's about the thread safety, you can imagine that now this run that we just have seen can be actually realized in many different ways. You would have type A here, where you would essentially have then this interesting different threads. And then suddenly you have an MPI again. When you have, let's say, a non-parallel region, you do MPI. But then, of course, suddenly you would have also basically the master thread also doing an MPI operation, which is now interesting. It could be then communicating, for instance, with another master thread on another node. So this is a, let's say, relatively straightforward way of doing it, but you can immediately say that it must not be restricted to the master. And then it becomes incredibly complex, as we see here with B, which we say serialized only one thread at the time, can actually do MPI libraries. And then with this communicate with another node, right? So you see, we spawn here threads, which is a very dynamic entity, and suddenly we let one of the threads, not the master thread that we kind of can control better and understand better, some of those threads is suddenly doing MPI. And immediately you can imagine you can have also something we call MPI thread multiple, that any thread at any time can do calls to the MPI library. And now basically then the MPI library will ensure that this is kind of thread safe, but it will be also very slow. And thinking about that, you also want to understand your code a little bit what it's doing, right? Then this is, of course, a very complex way of doing it this way. So the different options, I didn't picture here one MPI thread single. D is meaning essentially just an MPI only application. But in the initialization, you would give this and basically then have to adhere to what you just defined, which of these thread safety implementations you really want to do. So when you then do this multi-threading, basically beyond the MPI limits, it's the only way how you do it, which is not completely true today. Of course, you can also do some accelerators and some CUDA along the way, what basically many people do. But if you really want to do fine-grained parallelization, you really have to do then this OpenMP compiler directives in combination with an MPI program. And essentially then this OpenMP master thread is becoming this T0, which essentially is our rank that we know from the MPI process world. So then you would have to need basically different maximum number of threads for certain regions to make it a bit more, let's say, realistic to understand what's happening really, because you have now different levels of parallelization really. It is extremely useful for compute-intensive loops. We had this already, essentially in lecture 6. This loop support is, of course, quite neat, especially if it's a very independently parallel loop to be computed. Then, of course, what you have to think about that some of the MPI parts are then very pure MPI parts and others are very hybrid parts. And there you can imagine that there are different ways how you can do this now, this hybrid way. And we call that a vector mode and a task mode, and I will make a case for it. And of course, this means essentially they differ essentially in the degree of how the interaction between MPI and OpenMP is essentially existing. So here we have an example of a hybrid vector mode implementation, and directly, immediately, students might say, oh my God, we talk about Fortran codes. right? I just gave this example here in this one lecture to show you that actually application codes in Fortran are real in HPC. We put the most emphasis in your assignments, of course, on C programming, so don't worry about this. Just to let you know that when you go into the HPC field, maybe in some computational fluid dynamics or so, then you will see in some of the application lectures as well that Fortran is still a very active and lively programming language that is used in HPC. So, and actually there's MPI supporting it as well as OpenMP. So you see here a very, let's say, trivial example. Again, starting with an OpenMP parallel region of doing something we call the Jacobi methods that we will also review later. And then essentially you do basically an halo exchange and then communicate with MPI as we already know. So we have still the normal OpenMP work sharing constructs that we require for perhaps some compute intensive loops. And then essentially in the hybrid vector mode, we would say that the MPI calls are really outside OpenMP parallel regions, right? You see this very clear with this gray boundary. And this is how you, perhaps in an exam question as well, can very quickly determine that this is a hybrid vector mode, right? So here we see this is a parallel region in terms of threads. And here I do something with MPI parallel, send receive messages. So this is really something which we would say is a clean way of doing it. Of course, you can also think about this way, which is a hybrid task mode implementation, which is this task mode, meaning that essentially you can have MPI calls inside an OpenMP parallel region. You see this here very well, I think, when you think about what you learned about Sentinels. Even if it's Fortran, I guess you can immediately make the connection what we had before in C. There is a parallel region here. It's not gonna ending here, so it's actually going down all the way down here to the end of the parallel region. We have a short barrier here, but that doesn't matter. In the end, the point is that all of this is a parallel region in terms of OpenMP. And within this parallel region now, I do some MPI calls here, basically to get essentially the halo data from the neighbors. We will also review this later, why we do this, how it has to do with iterative methods, stencil methods. But here the message is really, it's quite complicated. It is quite useful, however, if you have really functional task compositions. So each of the parallel tasks is doing something completely different than there. It could be quite useful to have this task decomposition. Maybe one of the task decomposition would be from the functions. One is just caring about the data, right? To ship it between the different nodes, while one is more computing and so forth. So different ways how you can do this functional task decompositions. And it also nicely enables the decoupling of communication and the computation. Another point I wanted to do, especially with this Fortran code, is really, which we also see then in later lectures, like the CFD lecture, for instance, that Fortran has still, as it is here alluded to with the Twitter, quite some fans. If you go to this interesting, let's say, source, you see that Fortran is still alive, not mostly used in software engineering today, and used basically in terms of teaching, where many people refer to Java, C# today. And Fortran is quite old, but still is actually in a wide variety of codes available. However, the main key away message is really from this hybrid task mode. It is leading to enormous complexity in a large HPC application program, right? So that's why we need to do a comparison here really of these two modes and really think about what we really would recommend. And of course, you can imagine, I guess already when you had these two examples now, that vector mode seems to be intuitively really the one that is recommended. You have no real disadvantage by doing it. It's of course less flexible than the task mode, but still you have an independent, clean programming of OpenMP and MPI, which gives you a little bit simplicity, right? When you think about, you have an application domain problem to solve, the parallel computing is just a helper in this process. So in this sense, it's much more straightforward to program and to really enable a cleaner code. And you can really independently program this. So there's not directly a connection. Of course, probably on the data side there is, on the domain decomposition there is, but you don't really twist this as you have seen essentially in the task mode. And this is something what we would recommend. And really, if you're a complete expert in HPC, then there's no problem maybe of going to the task mode area. But this enables you, of course, being completely flexible in a way to take really the most out of the systems. But it has so many disadvantages that only experts really can handle it. And also the time you have to invest to make it right is something to review, right? Especially if you think about maybe doing a pure MPI program then instead for larger scalability and so forth. So this is something to think about. Take it away for your future when you do HPC applications again. This is something what you, of course, have to keep in mind. A more deeper comparison of vector and task mode, some hybrid benefits are listed here. You see essentially you have in both cases a very good load balancing. Of course, when you do either or, you would still benefit from the additional levels of parallelism, right? You can in both ways, of course, use MPI between the nodes and OpenMP within the node. It's just a question of how complex this additional level of parallelism needs to be and if it's really benefiting. Now, what we have seen with the really fine-tuning of task modes is that you can do a very reliable overlapping of communication and computation. Right, so this is of course something to consider, gives you certain benefits, but it's really what we would consider really extreme fine-tuning. So only go into this route when you really know what you're doing. We have here a lot of different other benefits that in both ways are actually not really a big difference if you combine and actually compare then this different vector and task modes. And you see here also, here and there, you have to have some acceptance when it comes about synchronous communications, when it's about, saturate the network. But in the end, you have essentially the kind of ideas to really fine tune your application to an extreme order of degree, where you then have certain thread core affinities involved. You have different overheads to think about. And something really to take more time if you really want to do this hybrid programming. I encourage you to go to the different references, really check what that means. What is a CC NUMA placement problem, right? So this is already would fill quite a big lecture part. Task core mappings in general also are quite interesting to think about, and so forth. So you see mapping challenges are quite tough. There are different options for hybrid programming that we basically see here. We have, of course, again, the idea of how we can program this. If we have our thread 0 or master thread, this could be, of course, placed in a way that we have just one MPI processor per node, and then the rest would be essentially the threads, all of them leveraging then, of course, in the CC NUMA, as you know from the architecture here, the shared memory space, right? Which is really one giving this kind of network interconnect. And then you would do essentially this MPI process is then communicating with the other MPI process, which is essentially then thread 0, again, the master thread, combining then essentially all the different threads. However, you can have MPI process per socket if you want to exploit a bit more of your memory, of your threads and parallelism. You see here, now we have 2 MPI threads here per node, essentially 1 per socket, and they will both then be able to communicate with the others, essentially also in the different nodes. And it goes without saying that you can have OpenMP threads, so-called with different ideas now allocated with this kind of MPI. Some call it round robin, across cores in the node. So this is now where completely flexibility can be achieved. You have different, let's say, ways how you have here the master threads or the ranks. You know, basically they are round robin. They're not anymore per socket, as you see. And essentially then still, of course, they are able to communicate via the network with the other node. And then something like 2 MPI processes, then essentially per node. So do you see quite some flexibility in these mapping challenges, how you exactly now think about your application domain problem, what these threads are doing, how you basically interact in terms of the MPI. You remember that is your only way of giving data to another node and actually receiving data from another node, because OpenMP will be always limited to this gray space here. However, just a quick part before we close the first part of the lecture, application example. You see here lessons learned really as an example from this 3D Jacobi application from nearest neighbor and so forth is really think about what you're doing. You see here some examples where even if you do kind of the vector mode here, the number of nodes are increasing, or if you do the task mode here, essentially landing with the performance here in Gigabit Ethernet, this is not really convincing because you have much better, let's say, performance if you go directly to essentially those which have InfiniBand connects. That's pretty clear. And you see that essentially you have here the pure MPI with Gigabit Ethernet there. It makes a huge difference if you maybe employ then, as we said before, the task mode, which is really fine tuning. So you can achieve more there. But also in many HPC systems is InfiniBand already deployed. So the network interconnect is incredibly good. And there you see you have kind of diminishing returns, right? So all of the different InfiniBand tactics of combining either OpenMP with MPI or using pure MPI are so close together that there's a question if you really need, then of course the idea of working on hybrid programming. Essentially what I'm saying is it makes less sense rather work on perfectly scaling MPI code if possible, especially with InfiniBand networks. This is really something where you see you have perfect network interconnectivity, and there your MPI program maybe scales quite better. Of course, it depends heavily on your 3D domain decomposition or on your domain decomposition in general, right? On the application domain problem that you want to have to solve. And I have to say, of course, in the light what we have in the future with modular systems, we also have to think about that. We have to review these statements that I do here every now and then, also in the light of the fact that people are using now CUDA and accelerators, which might be an extension to the idea of using shared memory. If you think about that, every node has a certain number of GPUs now with device memory, things you don't really know by now because we have our lecture on GPUs just coming up. But of course, there's also, of course, new programming ideas that will come up that maybe make new ideas of this hybrid programming much better in the terms of performance. We already had this particular application example, which was a HPDB scan, and I think I'm not overdoing it in the lecture, now stopping to bring this up again and again. Just finally remember what we have done here. So we used really MPI with the dataset 1. This was basically then at some point in time breaking off or tail off in performance. And this is a good indicator then to think about shared memory, right? So when we then did the hybrid and dataset 2, we already see that even with the hybrid, it actually at some point tails off. And you see in terms of combining or comparing maybe the MPI dataset 1 with the hybrid OpenMP and MPI 1, we got much better performance here. But this is not given for every domain application problem. You really have to think clearly. You have to analyze it with performance analysis tools. That's something what we will see in lecture 8 coming. And then you basically know if your application is really scaling that well. As I said, also alluding quickly to what we will also talk a bit more about when we have GPUs. We all know already now there's a different way of using a CPU in combination with this kind of accelerators, having this many core systems with device memory. Of course, this enables new ideas of hybrid programming. When you think about that, you have normally some serial code and a CPU, and you essentially have then the so-called kernel function that you will upload to a GPU to execute, which you see here essentially with a parallel different many cores that will work on this problem, and then you come back to serial code. So the problem you would have there, of course, is waiting time, right? The CPU is not doing anything. It just uploads the data to the device memory, uploads the kernel, and afterwards comes back and, basically has lots of weighted or an unallocated CPU. So it is much more smarter, of course, to use a CPU in combination with a GPU, but immediately when doing so, you can also imagine this makes it even more harder, especially if you think about that the CPU might be exploited with OpenMP and MPI as well. And then you add the complexity maybe on CUDA, which is a Compute Unified Device Architecture programming model of NVIDIA chips. But basically, we will see soon that AMD and Radeon cards, they have a different way of programming languages in lecture 9. So just to leave you the message that hybrid programming can be done to an extreme today. And I think this is a good application example for it, which of course enables you quite good performance, but is an example of a code which uses CUDA in combination, so CUDA on GPUs, in combination with OpenMP, in combination with distributed memory with MPI. It's a particle in cell code, which is used here, and I just give you a short demo on this here, basically showing you that it's quite smooth operating, lots of computational complexity, but as you leverage, of course, extremely different levels of parallelization, one level of parallelization within the GPU, one level with shared memory, and one level with distributed memory. Okay, so much for the application example. And let us just quickly return now to the lecture, because this is essentially all I would have for the first part of the lecture. We break here for a couple of minutes and then return back to the second part of the lecture, which is about patterns.